We're going to decode something you probably do every single day without even thinking about it, making a phone call. It seems so simple, right? But underneath, it's powered by this massive global system that's been around for over 100 years. So let's unpack how it all works.
All right, let's just start with this question. You pick up your phone, dial a number, and a few seconds later, you're talking to someone on the other side of the planet. What is the magic that happens in between? Well, the answer is a fascinating, century-old engineering marvel that, honestly, built the foundation of our modern connected world.
To get what's going on, we have to look at the one core idea that defined the telephone system for decades. It's a really simple but incredibly powerful concept that makes a classic phone call totally different from, say, sending an email or a text.
And that's really it. When you make a traditional phone call, the network literally builds a temporary private road just for you and the person you're talking to. And for the entire time you're on that call, that road is yours. It's completely 100% dedicated to your conversation.
So what does this dedicated line really mean? In technical terms, how does a network actually build this private road just for your call? Let's dive a little deeper into the mechanics behind it all.
Now, the technical term for this, and it's a really important one, is a circuit-switched network. Think of it like an old-school switchboard operator physically plugging in a wire to connect you to someone else. Once that connection, that circuit, is established, it is reserved exclusively for your call. Nobody else can use it until you hang up.
And this whole process happens in three really distinct phases. First, there's circuit establishment. This is the network finding and reserving a path from you to the other person. It's like the network's brain figuring out the route before the phone even rings. Then, phase 2, data transfer. That's you, actually talking. And finally, when you hang up, you get to circuit disconnect, and all those network resources are instantly freed up for the next person.
Okay, so that's how one call works. But how do you scale that up to a global system that connects hundreds of millions of people all at once? Well, for that, we need to look inside what's called the Public Switch Telephone Network, or as you'll usually hear it, the PSTN. The PSTN is, for all intents and purposes, the global web of all these circuit-switched telephone networks. It is a gigantic piece of infrastructure that connects over 800 million telephones, and that includes everything from old-school landlines to the smartphone in your pocket.
Now here's where it gets really cool. The fundamental building block of this entire digital network is this tiny little data channel that flows at exactly 64 kilobits per second. That might not sound like a lot today, but that number is not random. It is the result of some absolutely brilliant engineering from Bell Labs, designed to be the perfect amount of data to capture and transmit the human voice.
And this basic unit has a name. It's called a Digital Signal Zero, or DS0. Think of it as the standardized slice of the network pie that's reserved to carry one phone conversation. Pretty much every digital phone call is built on top of this fundamental concept. And here's how they do it. This is how your analog voice, which is just a sound wave, becomes digital data. A process called pulse code modulation basically takes a tiny snapshot, or a sample, of your voice 8,000 times every single second. Each of those snapshots is then converted into an 8-bit piece of data. And if you do the math, 8,000 samples times 8 bits per sample, what do you get? Exactly 64,000 bits per second. It fits perfectly into that DSO channel. Of course, to handle millions of calls, the network can't just manage individual DS0s. That would be crazy. So it bundles them together into these bigger digital pipes. In North America, we use something called a T1 circuit, which bundles 24 of those voice channels. Over in Europe, the equivalent is an E1 circuit, which bundles 30 voice channels, and it also has 2 extra channels, one for all that signaling we talked about, and another for network maintenance.
So this dedicated circuit system is just fantastic for the constant, steady stream of data you get from a voice conversation. But as our world started sending more and more computer data, which tends to come in these short, irregular bursts, the limitations of this model started to become really obvious.
And here's the crucial point. If you reserve an entire 64 kilobit per second circuit just to send a short email or load a simple web page, that circuit is just sitting there, empty most of the time. You're paying for an entire highway lane, but you're only using it for a couple of seconds here and there. For data, it's just incredibly inefficient.
This exact problem led to a completely revolutionary idea: packet switching. The thinking went something like this. Instead of building one dedicated private road, what if we just chop our message up into a bunch of little pieces, put an address on each one, and then just toss them all out onto a shared public highway?
So now, each of these packets is like its own little independent traveler.
They get routed individually through the network, with devices acting like traffic cops, pointing them toward their final destination. And this means the network's roads can be shared by millions of users at the exact same time, which makes it way more efficient for the bursty nature of internet traffic.
So let's put these two ideas head to head. Let's do a direct comparison and see how this new approach, which is the foundation of the internet, really stacks up against the classic telephone network. This is really the tale of two completely different network philosophies.
And this slide really lays it all out, doesn't it? The PSTN's circuit switching gives you that dedicated path with a constant, super reliable data rate. It's perfect for real-time voice where you can't have any delays. On the other hand, the internet's packet switching shares resources on demand, which is highly efficient for computer data, but it comes with a variable data rate and the potential for delays or jitter. So one prioritizes reliability and the other prioritizes efficiency.
So who won? Which model won the battle for how we communicate? Well, the funny thing is, the answer is kind of both. We now live in this fascinating hybrid world where these two technologies not only coexist, but they're becoming more and more intertwined every day.
I mean, think about it. For more than a century, the PSTN was it. It was the only way you could make a voice call. But then the rise of these incredibly powerful and efficient packet switch networks completely changed the game, and that ended the undisputed reign of the old telephone system.
Today, your voice can travel in all sorts of ways. And while some of these early digital technologies just ran over the old phone lines, the real game changer was Voice over IP, or VoIP. That's the technology that takes your voice, chops it up into packets, and sends it right across the internet, just like it's an email or a web page.
And all of this leaves us with a final, really interesting question to think about. As the reliable old PSTN and the dynamic, flexible internet continue to merge together, what does that mean for the future? A phone call isn't just a circuit-switched conversation anymore. It could be a video chat, a VoIP call, a WhatsApp message. Our very definition of what it means to communicate in real time is evolving right in front of us.